Hello, in this video we're going to be looking at the second derivative test. The idea of this is seeing if we can use what we know about the second derivative in order to more easily determine what's going on with our extrema. Here is the second derivative test. So we're starting out assuming that the first derivative is 0. So both of these are saying that thing. If our second derivative is negative, that means we're concave down. That means it must be a local maximum. The reverse happens if we are concave up, then it must be a minimum. So I've got this first derivative. I want to find the local max, mins, and points of inflection. So I know I'm going to have critical values when this thing equals 0. So our critical values are when x equals 1 and when x equals 2. I also care about points of inflection. Points of inflection I need to find from my second derivative. So I got to find y double prime. So our potential points of inflection are going to be at 1 and 5/3. So what I want to do now is I want to put all of this information into a sign chart and see what's going on with my function. So I've got 1 is important for both the original function, for both the first derivative and the second derivative. 5/3 is going to be interesting. And 2 will also be interesting. I'm not going to space these out as it would be on a number line. I want room to be able to see what I'm doing. So we've got y prime, and then we've got y double prime. And we care about what signs are we getting from these things. So if we look at y prime, if we put in some number that's smaller than 1, like 0, we would get -1 squared, so that'll be positive, times -2, so that will be negative. So meaning we're decreasing. If we don't really care about between 1 and 5/3, it's really between 1 and 2. So I'll do like 1.5. And then that'll work for both 1 and 2, because 5/3 is for the second derivative, not the first. So it shouldn't make any difference. So if we do 1.5, this will be positive, but not by much. But when we square it, it'll be a kind of small number. And then this will be pretty negative. So these are also both negative. And then if we check 2, any number that's bigger than 2, so like, I don't know, 50, that'll be a big positive number squared, so positive, and so then that will be positive. Now let's see what's going on with our second derivative. So anything less than 1, so I don't know, 0, so that'll be -1 times a -5, so that'll be positive. So it will be concave up. And then on the other side of 1, between 1 and 5/3. So will 1.5 work? Yeah, 1.5 should work. So let's see. So 1.5 minus 1, so that's a half. 3 halves, that's 9 halves minus 5. That'll also be positive. That'll be like a half. So a -1/2 and a -1/2. -1/2 and a +1/2, that'll be negative, so then we'll be concave. If we check values bigger than 5/3, I can do whatever I want. I don't really care about that 2 because that's more important for that first derivative. So I'm going to do like 50. So that is 49, and then that's like 150. So those will both be positive. So both of these intervals, we should be positive. We'll be concave up and positive. So then we're going to be concave up. So we can tell right here that this is a liar point, that it's decreasing and decreasing, so that's not actually a minimum nor a maximum at that point. And then here, like by first derivative test, we can tell that is a minimum. But we could also take a look, since this thing is concave up, that's telling us that same thing. If we have a positive second derivative, then this thing has to be a minimum. We do get a point of inflection right here at 5/3 because we're changing from concave up concave down to concave up, and also one here at 1. If we wanted to write that all up in nice sentences, we can say that we don't have a local maximum because we never had that point where we were a max. We do have a minimum here at 2 that we just talked about because of that concave up. And we have points of inflection at 1 and 5/3. In this example, we're going to try to use that second derivative test to determine what's going on with our extrema. So what I have done here is I've already found the first and second derivative, and I want to figure out what are those critical values for this function. So I factored this negative out, and then did a little bit more factoring so that I can find those two critical values. So when x equals 5/3 and when x equals 3. Now, normally we'd have to make a sign chart to see what's going on at 5/3 and what's going on at 3. But instead, what I would like to do is plug those values into my second derivative and see what's going on with the concavity of those points. So if we do f double prime of, let's do 3 first, that will equal -6 times 3 plus 14, which equals -18 plus 14, which equals -4. So we have a negative second derivative. That means that f double prime of 3 is less than 0 at that point. If we're negative second derivative, that means we are concave down. And if we're concave down, that means that 3 is at the top of that mound, and 3 is a maximum. We can do the same trick with 5/3. F double prime of 5/3 is going to be -6 times 5/3 plus 14. That'll be -30 divided by 3, so that'll be -10 plus 14, which equals 4. So f double prime of 5/3 is greater than 0, so it is positive, and we are concave up. If we're a concave up shape, then it must be at the bottom of that thing, so 5/3 is a minimum value. At this point, we just want to figure out what is the location of those extrema, so we can just plug those two values, the 3 and the 5/3, into our original function. I've done that off screen, and I got 9 and -275/27. Again, I'm plugging that into the original function because I want to see where that minimum and maximum is on the original function. And then we would just finish it up with a nice sentence. F of x has a local maximum at 3/9, and has a local minimum at 5/3, -275/27. Writing those coordinate points and writing out our words. In this example, finding the relative extrema, I've taken the liberty of finding the first and second derivative of this thing. So I want to first find my critical values. So I've got to do a little bit of solving over here. So first thing I want to do is set my first derivative equal to 0. I'm going to multiply both sides by x squared in order to kind of clean up my problem. It makes it pretty easy to solve. Then I just got to add the 4 and square root both sides. And so we get our critical values of plus or minus 2. I want to know if these things are going to be maxima or minima or both. No, they can't be both. But just plug it into the second derivative. So let's see what f double prime of 2 is. So that's going to be 8 over 2 cubed, which is 8 over 8, which is just 1. So f double prime of 2 is greater than 0, so that means we are concave up. And if we are concave up, that means we have a minimum value at 2. Next, let's check that -2. So f double prime of -2 equals 8 over -2 cubed. So that'll be 8 over -8, which is -1. So now f double prime of -2 is less than 0. So we are concave down. And by the second derivative test, f has a maximum value at -2 because we're concave down and it's going to be at the top of that arcy thing. And that's pretty much it for this problem. The last couple steps are pretty easy at this point. We want to figure out what our actual locations of these extrema are. So I'm plugging 2 into the original function and -2 into the original function to get 4 and -4. And then we just want to write those coordinate points and what they are. So F has a local minimum because, again, we are concave up, and that is the minimum point. It is the bottom of the U. And then F has a local maximum at -2 because it is concave down at that point, and it has a first derivative of 0, and it is that maximum point. That is it for our video on the second derivative test. Remember that the second derivative assumes that you've checked the first derivative to make sure that it was 0. And then if the second derivative is negative, we get a maximum. If it is positive, then we get a minimum. This is just like a quality of life option as you're trying to determine if you have a maximum or minimum. You can still use a sign chart in the first derivative test in order to figure out if you've got a maximum or a minimum, but sometimes it might be easier to look at what's going on with the second derivative. Thanks for watching. Hope you took some good notes, and I will see you next time. Bye-bye.